So where we left off last time, we're solving equations and we talked about consistency equations. Those are equations that have a finite number of solutions. We have identity equations that have infinitely many solutions, or all real numbers is what I should say. And then we have what are called inconsistent equations or equations with no solutions. And that takes us through section 1.4. Now, section 1.5, we're getting into story problems. And I think pretty much every algebra class you ever take, they have a section like this, where they want to give you some advice on how to solve problems. So what I'm going to do, I'm going to give you the advice that they have. And the thing I'm going to tell you is the difference between story problems and regular reading. When you read a news story, most things we read are fairly, I guess you could say, linear. You go from this to this to this to this. And there's this, you get a picture of what's going on. The mystery is answered as you read. So that's what happens when you normally do any kind of reading. Like if you're reading a news story, there's a big mystery, and as you read more of the story, the mystery sort of solves itself. Math stories aren't like this. They read very differently. You're going to have holes in the story. And you can almost think of it as sort of like maybe if you're reading a mystery novel or something like that, a whodunit kind of thing. And you get a picture of what's going on, and then that's about it. Not a picture of what's going on, but you get a picture of something that's happened, but there's gaps. So you have to do a little bit of Sherlock Holmes. Take what they gave you and then try to fill in the gaps. So again, story problems, if they read differently, if they're kind of surprising the way they read, you're not the only person knowing that. They're written that way deliberately. And unlike regular stuff we usually write where all the information we need is there. So I want to talk about the 5 tips that they give for how to solve these. How do you break down these mysterious kinds of presentations? And this is coming from page 54. So number 1, what you want to do is read the question until you understand it as best as you can. Now, how do you know you've understood something? Well, what you want to do, read it enough times. So you might not have to, you're not going to get it necessarily the first time. And what you're looking for is you want to identify knowns and unknowns. And again, if you're just joining us, my car didn't start this morning, so I'm doing the lecture from home using the studio I put together last semester when we had to suddenly switch over from classroom teaching to the online teaching. But that's the idea. You want to read and reread until you can identify what is known and what is unknown. And that's a big difference with, like, again, like a news story or something, or a poem. They're going to not have any unknowns in there. But in this case, you have this new kind of character that's going to show up in the story, so to speak. The unknown, the missing piece. So that's the first thing. And then I'm going to put a little caveat there. Let X represent the unknown. So we're going to let x be the unknown. Now, there are some expressions, or there are some things that are dependent on the unknown. And we usually get them in the form of expressions. And I'll give you an example to go with this. But we want to write any expressions depending on the unknown. So what you might have is something, for example, let's say you are accumulating, say, money. You're earning money. And you have an unknown amount that you started with. But then in the last 2 days, you've gotten $100. So that means the total amount you would have would be the $100 you've picked up in the 2 days, plus whatever you had started with, that unknown. So this would be an expression describing the total amount of money you have in your account. What was in the account in the beginning, which we weren't told, plus the $100 you've earned in the last 2 days. So this would be an expression depending on X. I'm going to do a full example. We will do one for sure. So number 3, we'll find and write an equation for X. We'll find and write an equation for X. Now this depends on the problem that we're solving. There's going to be some kind of relationship that's going to give us an equation. And sometimes this might require a little bit of outside knowledge. So we might need a little bit of outside knowledge. For example, if we're working with, say, like investments, how do you compute percent growth, like percent increase or percent decrease? Sometimes we'll get a little bit of outside knowledge that's necessary. So number 4. Once we have our equation, we're going to solve the equation. And that's just using the techniques of algebra we looked at last time. Finally, what we're going to do is, to the best of our abilities, we're going to try to check our answer. So we'll check the answer. And the way we're going to do this is we check it against the wording of the original problem. Abbreviate problem there. We'll check the answer against the wording of the original problem and see if it makes sense. Now, usually we mean check answer, we mean we're going to check our calculations. And that's not a bad thing to check too. There's nothing wrong with that. I mean, make sure you didn't make an arithmetic mistake or something like that. But one of the things you want to be careful of is that you can do all your calculations correct, but the method we use to solve the problem might not have been the best method. And how do we check that? So what we'll do is we'll read the problem and then look at our answer, and does our answer make sense? Now, sometimes you can't really check if you use the best method. The only thing you can do is maybe ask someone who's solved a problem like this before and see if this is the way they've done it. But if you get an answer that doesn't match up with the problem, for example, if you're doing something with temperature and it has to do with cooking, say, a turkey in an oven, and the answer that you get for your problem is 10,000 degrees Fahrenheit. That's going to be a little suspicious because there's really no good reason if you're trying to figure out at what temperature you're supposed to cook a turkey in an oven. You're not going to need 10,000 degrees. That would be ridiculous. This has to be some special kind of turkey that, well, anyway, something really impressive, I guess. Maybe made of some unusual metal. So if you get a real kind of bizarre answer, given the problem that you're trying to solve, that could be a clue that your approach, there's something in the approach that's not correct. Even though you've done the calculations right, there's something in the approach that's just not right. So let's do an example. Let me pull an example here from the text. And let's see here. All right. So I'm going to look at example 4. It's on page 59. But this is what we've got. And I think I have a storm coming through. So if I get cut off or the internet connection gets bad, that usually happens when storms come through, I've noticed. So let me know. I mean, if I start kind of fading out or something. So we have a problem where there's a 40% price reduction. Now, suppose after the reduction you paid $276 for that camera. What was the original price? So you have a camera, it's basically 40% off, and you get this camera for $276, and you're sort of wondering, well, what did it actually cost from the get-go? What was the original price? And what we can do, we can want to look at this problem and try to figure out, well, what's missing? What are we looking for? What's the missing part? Now, in this one, they it's hopefully not going to be too obscure when they do these problems, but sometimes it can be. Now, this one, what they want us to look for is the original price. So we can give this another scan just to make sure there isn't something else they want us to look for. But they want us to looks like it's just the original price this time. So for number 1, let X be the original price. So that's the thing that's unknown. That's what we're looking for. Now there's other information that is known. The percent discount. That was 40%. What else do we know? The sale price. This is after the discount. It's $276. So we've got that much figured out. So that's what we know, and this is what we don't know. So we take that problem that was this sort of little tale of getting a camera on sale at the store, and we reduce it down into what we don't know and what we know. So in a sense, we sort of rewrite the problem in terms of unknowns and known. So we think about step 2. Are there any expressions we can think of that depend on the unknown? And this is where some outside knowledge can come in. We can use this for the equation as well. But when we compute like a sale price or the amount of a discount, the discount is the percent times the price. That's the amount of the discount. Now in the textbook, they actually skip this step, but you could say that we could actually think about this. The amount of the discount itself, it's percent times the price. So again, this is some outside knowledge that they sort of assume you would understand when you do this problem. And I mean, if you don't, send me an email. Let me know if you have any questions about this stuff. So how do we do that in our case? Well, the percent was 40%. And then the price, well, that's X. We didn't know the price. So the way we write this, the amount of the discount is 0.40 or 0.4 times X. So this is the amount of the discount in actual dollars that we received. And I'm using the dot here for multiplication. So now we go to step 3. We want to come up with an equation. So for step 3, if we think about how sales work, the sale price is the price minus the discount. So sale price will be price minus discount. Now we have the sale price. That's what we paid $276 for. But that's what was the $276. The price is unknown, and the discount is 0.40x. Still multiplication, I'm just leaving the dot out of there. Now, we can solve this equation, and the way we know we can solve it, we have an equation with one variable. So this will be able to solve. So x minus 0.40x That's 0.60x. Then we can divide both sides by 0.60 or 0.6. And what we'll get is x is $460. So any questions about that so far? The last step in step 5 does the answer make sense? So if we reread the question, a 40, basically what we can say is this. A $460 camera was on sale at 40% off for $276. Does this make sense? Does this seem like a reasonable outcome? And it kind of does in a way. I mean, first off, it's a sale price. So we would expect that the original price is more than the sale price. And 40% is a pretty good amount of money you're going to get a discount on. So we should see a significant decrease from this original price to the sale price. And if we want, we can still check our math. We can see if this is making sense. So if you think about how to calculate 40% of 460, well, that's going to be $184. So we're going to get 40% off. So that means we subtract $184, which is our 40%. And sure enough, we get back 276, which was the sale price that we paid for. So it seems like a sensible answer, and using sort of what would be an intuitive approach of calculating 40% off, sure enough, we get the price we paid for. So this looks good. So 460 seems like a good answer. So let me do another one. So I'm looking at number 5 on page 61. And like a lot of math, these are just going to take practice. Practice breaking them down, practice solving the equation. It just takes some practice. Now, the length of the American football field is 200 feet more than the width. So if the perimeter is 1,040 feet, what are the dimensions of the field? And this is including the end zones. So the field has a length 200 feet more than the width. What are the field's dimensions if the perimeter is 1,040 feet. Now, I'm actually rewriting this. It's not the exact text they used in the book. And that's another technique with doing story problems. If you want to rewrite the problem so it seems to make more sense, do that too. Sometimes that helps. So that's the situation we're looking at. So number one, what's unknown in this and what's known? Now this is kind of interesting. We don't know the dimensions of the field. So I'm going to call L the length. I'm going to call W the width, because they want us to find the dimensions. That's the length and the width. Now, one thing we do know, length is 200 feet more than the width. We know that. We also know the perimeter is 1,040 feet. So this is the information we know, and this is what we don't know. Now, if you wanted to, you could take this a little further with the known part. We also know this is a rectangular field, and that there's a formula for perimeters of rectangular fields. I'm going to bring that in later, but you could list it here if you wanted to also. And that fully sort of expands out this problem into what we don't know and what we know. Now let's look for some expressions. Well, is there anything that depends on L, the length, and W, the width? Well, oddly enough, they depend on each other. We're told that the length is 200 more than the width. Now, 200 more, that's one of those phrases that we saw earlier, where 200 more that's 200 plus something. It means add. So let me say the length is 200 more than the width. It means L is 200 plus whatever W happens to be. So any questions about that? And again, I'm doing this a little bit differently than what they did in the text. But here's an expression, or actually a formula outright, for the length in terms of the width. There's a relationship that we can see between the unknowns in this case. So now we go to step 3. This is when we try to find an equation. And we're going to use some outside knowledge. We're going to use our knowledge of perimeter. So last time we needed to know how to compute a discount. And from a discount, use that discount to come up with a sale price. Here we're going to use perimeter. Now the perimeter of a rectangle is 2 times the length plus 2 times the width. Now we've been told what the perimeter is. It's 1,040 feet. And we've been told what the length is. It's 200 more than the width. Now we don't know the width. But it turns out that's going to be okay. The reason it's going to be okay is we have an equation, there's an equal sign, and there's only one variable. So that means we can solve for this variable. So I'm going to distribute 2. And if I combine these like terms, I'll get 1040 is 400 plus 4W. And so that's going to be the equation we're going to solve. So finally, in step 4, so to solve this equation, we're going to get W by itself. So I'll subtract 400 from both sides. We get 640 equals 4W. Divide both sides by 4. We'll get 160 equals W. So that solves one of the unknowns, but we're not done yet. We still have to find the length L. That's one of these things to keep an eye out for in this type of a problem. We'll solve for one unknown, but we need to find the second. Now recall the expression, or actually the formula we found. The length is 200 more than the width. Well, now we know the width is 200 plus 160. Well, that means our length will be 360. And now we have our unknowns. We're all done. So the next thing to do is to check the problem. Does the answer make sense? Now we usually check it against the wording. So the length was 360. The width was 160. And the perimeter was 1040. Now the perimeter is the length all the way around the rectangle. So we would expect that the length and the width would be smaller than the perimeter. So far this seems to make sense. Now we do have a mathematical check. If we take 2W plus 2L, or 2 times 160 plus 2 times 360, what we're going to get is 1040. So if we try to calculate the perimeter from scratch using our value for width and for length, we get our perimeter. So any questions about that? So that's the thing with story problems. Again, what I would say is don't let them surprise you. They're written in a very unusual way. They're written with, it's a little story with gaps in it. And it doesn't always make sense why you would have those gaps, but it's kind of a murder mystery kind of thing. Like, you ever play those games? Or think of the riddles that you have Gollum down in the tunnel and you're telling the riddles with Gollum, and you've got to try to figure out what's going on, and you say Gollum doesn't eat you, and you're trying to put the pieces together to find out what's the whole story. And a good way to do that, read the problem well enough so you can identify the knowns and the unknowns. And don't be afraid of the unknowns. Give them an identity. Call them X, call them L, call them W. And then list what you know. And those two lists, the unknowns and the knowns, that's another way of just rewriting the problem so it's a little more sensible. And then sometimes you have to bring out some outside information. You might need to know how to calculate a perimeter or how to calculate a discount. So that can come up too. So the other topic in this section, it's working with formulas. And what we're going to be doing is solving for one variable in a formula. So how does that work? Well, what we're going to do, treat other variables as constants. Now, this could be kind of a strange idea because a variable, well, it is a number, just like a regular constant. It's just an unknown number. But we're going to move these variables around until we get the unknown number that we're looking for by itself. Let me give you an example. Let's say we're going to solve for b, and we have this formula. So how do we do that? Well, what we want to do is we want to get b by itself. So we can take our formula. To get b by itself, we need to get rid of this c. B's feeling kind of, I don't know, it's kind of a stormy day today. So maybe it's one of those days where you just want to sit next to a window with your favorite book, have a cup of tea, stare out the window, and you know, talk to your friends later, but maybe not today. So you want to be by yourself. Well, B wants to be by itself. So C, we're going to move C by subtracting and canceling to the other side. So we subtract C plus C, this will cancel. Now we get A minus C over here. Now this is kind of strange. What's A minus C? What do you do with that? Well, the thing is with variables, they're numbers, so we can subtract them. That's totally fine. But we can't actually do the computation until they are identified. If they're not identified, we're just going to leave them. We'll just keep it as A minus C. We'll be in a holding pattern until someone tells us what A is and tells us what C is. All we're going to do is write this little note, so to speak, that we're going to subtract C from A. And we'll just leave it like that. But in the meantime, B is by itself, so we have solved for B. And that's it. Questions about that? So let me do a couple more of these. Let's see, let's solve for H. Now for this one, it's a little trickier. because we have two things multiplied to h. H just wants to be by itself for a little bit. So we have a pi and an r squared. Now what we can do, we can think of pi r squared is having parentheses. Now the reason I'm doing this, it has to go back to that stuff about commutative, associative. This is the associative rule. It says, well, should we multiply pi, r squared, and h? Do we do this order, or maybe do we do it in this order? Do we multiply these two first, or maybe these two first? It doesn't matter. With multiplication, doesn't matter the order, it doesn't matter how you group them. And so that's where those rules kind of help. So I'm going to take this piece multiplied to h. So now I'm going to do something else. To get h by itself, I'm going to divide off this entire piece, this entire pi r squared. And by doing that, because the opposite of multiplication is division, I'm also going to divide, and because what I do to one side, I have to do to the other. So if I divide this side by pi r squared, I have to divide this side by pi r squared. Now this side only has that one v. So what this means is I'm going to divide v by pi r squared. So this will cancel because multiplication and division are opposites, or multiplication, division. And then on the other side, I just leave it like it is. And for the same reasons as before, I don't know what v is, I don't know what r is, so I'm just going to leave it like this until someone comes along and tells me what v and r are supposed to be. So any questions about that? Let me do one more. So A equals P plus PRT. Now this is kind of a tricky thing because we got P in two places. How do we get P by itself? Well, let me share with you a trick. We can rewrite this as P times 1 plus P times RT. And rely a little bit on your mathematical experience. We got P in two places. This looks like P's been distributed. So let's reverse that distribution. So if you think about this, if we go P times 1, P times RT, like we're distributing, we're going to get the original equation. But the good news is we're down to 1P, or P in one place instead of being in two places. Mathematically, it's the same thing. That's kind of the neat trick with reversing a distribution. Instead of having it in two places, you get P in one place. And that makes this a lot easier. So what we have here, we have p times this entire piece. So what we can do is the opposite of that. We'll divide this entire piece. But what we do on one side, we got to do to the other. So we got to divide this other side by this entire piece. So what that's going to give us, multiplication, division are opposites, they'll cancel. We'll get A over 1 plus RT equals P. Now, when we have these compound fractions, well, not compound fractions, but these more complicated fractions, or rational expressions, as they say, we don't have to have the parentheses here anymore. These expressions automatically place parentheses on the bottom and on the top. So it's really a kind of convention that we would write our answer like this. Sort of like we have multiplication implied when you have 3x, like 3x's, 3 times x. In mathematics, there are also implied parentheses here. So we don't have to put these. In fact, they might even mark it wrong if you put them in there, though technically it's not wrong. But that would be your answer. Any questions about that? So what we're going to do, section 1.6, we're getting into exponents. And exponents are really a kind of shorthand. So we're going to learn how to manage all these exponents. Now, exponents, again, they're shorthand, like 5 to the third, 5 times 5 times 5. That's 5 to the third. So let's say we have something like this. 5 to the third times 5 squared. Well, we have 5 times 5 times 5 times 5 times 5. 3 5s and then the 2 5s. But if we count these, there's 1, 2, 3, 4, 5 5s. Oh dear. Now, what we're looking for is a shortcut. We don't want to have to keep writing all these out and then counting them up. So we're going to notice something. To get this number, we just have to add those two numbers. And so this is what's called the product rule. If you have b to the m times b to the n, this will be b to the m plus n. We just have to add them up. So I'll do another example. So let's say we're going to do this. Well, we can combine the 6 and the 5. It'll be 6 times 5. And then we have x to the 4th times x squared times y cubed times y to the 7th. So I'm going to group the variables into x's and y's. Now this here is 30. This here, though, using our product rule, is x to the 4 plus 2. And this one here will be y to the 3 plus 7. So what we get is 30, x to the 6th, y to the 10th. And that's going to be our answer. Any questions about that? All right. So that's how you use the product rule. Now let's say you have this situation. Let's say, 6 to the 5th over 6 squared, or 6 to the 2nd. Well, this is 6 times 6 times 6 times 6 times 6 over 6 times 6. Now, we have some cancellation going on. So we can cancel a pair of 6s here. We can cancel a pair of 6s there. So what we're left with, 6 times 6 times 6, or 6 cubed. Now, let's take a look for a shortcut. If we look at our answer, we get this number by subtracting the bottom number from the top number. So this is what we call the quotient rule. And it works like this. You have b to the m over b to the n. It's b to the m minus n. So let me give you an example. Now, again, we're going to group things up. We can think of this as 30 over 5 times x to the 12th over x3 times y to the 9th over y to the 7th. And as you recall multiplying fractions, you just multiply, you get 30 times x to the 12th times y to the 9th, which is this right here. And then 5 times x cubed times y to the 7th, which is this right here. Or if you wanted to, you could just rewrite it and just note that we have the x's, and then we have the y's, and then we have the constants. And you don't have to break it up like this. So you could just sort of circle, like, okay, here's the x's, here are the y's. And if they're not written where one's on top of the other, you could rewrite it so it is. And then you do your divisions. So 30 divided by 5 is 6. This one here will be x to the 12 minus 3. This one here will be y to the 9 minus 7. And the result, we'll get 6 x to the 9th y squared. And that's going to be our answer. So there's something that comes out here. Let's let B be any non-zero real number. So let's say we have this. B to the n over B to the n. Well, we're dividing something by itself, like 3 divided by 3. Well, that's always equal to 1. But we also know that we can rewrite this as B to the n minus n, or B to the 0. So if we do our little shortcut, what we'll find is that for any non-zero number, B to the 0 is equal to 1. Now, the reason it has to be non-zero is that if B is 0, we're going to be dividing by 0, and that's undefined. So we have to have non-zero for B. Now, let's say we have this. Well, we can write this as 5 times 5 times 5 over 5 times 5 times 5 times 5 times 5. And I'm going to put in a times 1. And I'll show you why. Because I can cancel these, I can cancel these, I can cancel these. I wipe out all the 5s on top. So whenever I do that, I'll do a times 1. Because we're going to lose everything up top. What we'll get is 1 over 5 times 5, or 5 squared. Oh, I'm sorry, not 5 squared. Ooh. 1 over 5 squared. Well, all right, that's nice. But let me do this another way. We can call this 5 to the 3 minus 5. Again, we subtract the bottom from the top always, no matter what numbers we're dealing with. And this comes out 5 to the negative 2. So now again, we have two answers. The first answer we got was 1 over 5 squared, and this is equal to 5 to the negative 2. And so this is how we handle what are called negative exponents. So just to maybe write that a little bit differently, it's a little clearer. You get 1 over 5 squared, which was equal to 5 to the 3rd over 5 to the 5th. And we also got 5 to the negative 2. Hence, 1 over 5 squared must be equal to 5 to the negative 2. That's the more mathematically complete way of concluding this. So that gives us our negative exponents. So let me give you an example. Or here, so in general, what this is for negative exponents. So b to the negative n is equal to 1 over b to the n. And again, we want b not equal to 0. Now you can have 0 to an exponent, that's totally fine, just not for negative exponents. So for example, let's say we have this. What we want to do is we always want to rewrite these with positive exponents instead of negative. So this will be 1 over 7 squared. This will be 1 over 4 cubed. So we're dividing 1 over 7 squared by 1 over 4 cubed. We can treat these like fractions because they are fractions. We do our KFC, if you've heard that. You keep the first fraction, flip the second one, and for the C, you change division to multiplication. So KFC. And we multiply across. We'll get 4 cubed over 7 squared. And 4 cubed is 64. 7 squared is 49. And that's going to be our answer. Questions about that? So let's take a look at another one here. Let's say we have this. Oh, sorry, let me put my chat on there. I didn't have my chat. There we go. So we have 5 squared to the 3rd power. So what this means, this is 5 squared times 5 squared times 5 squared. Whatever's in here, we have 3 of them multiplied together. Whatever this is, if it's simple or complicated, we're going to have 3 of them multiplied together. Now we use our rule, our product rule. So we add the exponents. Now again, we want to look for a shortcut. And so what we see is this. We want to get this number from these two. Now, last time with the product rule, if you had 5 to the 2nd times 5 to the 3rd, you would add the numbers to get 5 to the 5th. But we need to get 6. And the way we get 6, we multiply those two numbers together. That'll give us 6. And so what we get is the power rule. And this is when we multiply the two powers. So let me do an example. So what we're going to get here is b to the -4 times -2, and that's going to become b to the +8. Any questions about that? So now let's consider this. This is 2x times 2x. Here, for the sake of space, I'll make this a 3 times 2x. So you have 2x to the third power. So what we'll get is 2 to the third. So we have 1, 2, 3 2's multiplying, and then x, 1, 2, 3 x's multiplying. So again, we're looking for a pattern we can follow. And what looks like we just need to do is just distribute the 3 to the 2 and the 3 to the x. And sure enough, that's going to be the pattern that works. So this one is products to powers. So AB to the n is A to the n, B to the n. So let me do an example. So in this case, what we're going to distribute is this -2. So we get -3 to the -2. We're going to get x to the -1 to the -2. We'll get y to the third to the -2. And then here, what we're going to do, we're going to use our products rule, or power rule, I'm sorry. So we'll get x is -1 times -2. This is y to the third times -2. Now this one, it's got a negative exponent, and we want to write these without negative exponents. And by the way, you need to put parentheses there. There's parentheses on this -3. That's very important. We want the parentheses on that -3, the negative included. So to write this without the negative, this will be -3 to the second power. So I'm just going to circle this because we're going to modify this. That's what we end up getting in our first step, second step actually. Yeah, that negative in parentheses is very important. Now, -3 squared. -3 times -3. Two negatives will multiply to a positive. We'll get +9. This will be -1 times -2, get x2. And we get y to the -6. Now, we can rewrite this as 1/9 times x squared over 1. And since this is negative, we can rewrite it without a negative by flipping. And now we multiply across, we'll get x squared over 9 y squared. I'm sorry, y to the 6th. Questions about that? So there's one more rule. I'm going to go a little long today. I just want to get through 1.6. There's one more rule, and then I just want to do one other example other than the one for the rule. And then that's it for today. We'll be done. But let's say I have something like this. Five-thirds quantity squared. Well, this would be 5/3 times 5/3, or 5 times 5 over 3 times 3. We'll get 5 squared over 3 squared. So if we're looking for a shortcut, it looks like we just distribute the 2 to the 5 and to the 3. And that's correct. If I'm going too fast, let me know. So in general, this is called the quotients. To powers. If a over b to the n is a to the n, whatever a happens to be, and b to the n, whether b happens to be, even if they're expressions, they're going to be to those powers. So for example, x cubed over y squared to, we'll just go with the positive form. Well, what this is saying, here, just to let you know, a is x cubed and b is y squared. So what we're going to get is a to the 4th, or x cubed to the 4th, and then y squared to the 4th. And so if we use our, let's see, our powers rule, or power rule, we'll get 4 times 3 is x to the 12. And then 2 times 4 is y to the 8. And that's going to be our answer. Any questions about that? So I'm just going to do one example here, and then that's going to be it. We'll call it a day. And this is kind of a hairy one, if you will. Kind of brings all this together. Well, for this here, we're going to use our quotient rule to distribute this 2. So we're going to get this. We distribute that 2. And then we distribute the 2, not for just the quotient, but now for the products. So we get 25 squared, x squared, squared, y to the 4th, squared, and then minus 5 in parentheses, because we're going to square the minus and the 5, x to the 6th squared, y to the minus 8 squared. Now let's see, 25 times 25. What would that be? I don't have that one off the top of my head. Let me see. $6.25. So what we'll get is $6.25. 2 times 2 is x to the 4th. We're multiplying, we're not adding. Y to the 8th. And then this is 25. We have x to the 12th. And then y, we're multiplying to the negative 16. Here, I'll rewrite that so you can see it. Now we've got the x's and y's all lined up. So we can just do our divisions. 625 divided by 25. Well, that's just 25, because 25 squared gives you 625. This will be x to the 4th. And we always do the top number subtracting the bottom number. It doesn't matter which one's bigger or smaller. It's always top minus bottom. And this is going to be 8 minus negative 16. Or 25 x to the negative 8 y. Now, double negatives become a plus. So 8 plus 16 will be 24. So I can think of this as 25 over 1, which you can always do, times. Now for x to the minus 8, I'm going to rewrite that as x to the 8 using my rule for negative exponents. And this is y to the 24th over 1. Multiply it all together, and we're going to get 25 y to the 24th over x to the 8. And that's our answer. Any questions about this? There's a lot in the exponents. You have a whole bunch of rules there. So when you do your homework, kind of be careful not to confuse. It's easy to do. Product rule with product the powers rule, things like that. And just the powers rule itself. But we're almost done with chapter 1. We'll get through section 1.7. And that's scientific notation. We'll look at that on Thursday. And that's just another way of writing numbers with lots and lots of zeros in front of them or behind them. But that's it for today. If any questions, let me know. I'm going to post this video later and I'll send a message out. It'll be posted on the YouTube channel. And other than that, have a wonderful afternoon.